Let us wait for some more time. Let others join. Maybe after a couple of minutes, I will start. All right. Anyway, we will start. It's already 6:05. Can you please confirm that you can hear me and see the screen? Can you see the screen and can you hear me?
Yes, we can.
Okay, we'll start. So, this is the third session of the doubt clearing classes of the course Fundamentals of Electrical Engineering by NPTEL. The instructor is Professor Debupriyo Dash from IIT Kharagpur, and I am Saptarshi De. I'm a PhD scholar at IIT Bombay, Department of Electrical Engineering. I work on machine design for my PhD. And there are three doubt clearing sessions every week. I take this one every Monday, 6 to 8 p.m. So in this, we will cover in today's session, we'll cover the materials of week 3, which is termed as DC network theorems. Can you guys quickly tell me which all theorems are covered in this week's lectures?
Sir is currently like in all the three lectures, sir has done mesh analysis and node analysis.
Mesh and node. So Norton and Thevenin are not yet covered.
No, sir. And he was telling about super mesh also, which is covered in that.
Superposition or super?
Super mesh, super mesh.
Okay. Anyway, so this mesh node and what we will always require for any circuit is KVL, KCL, and maybe at later stage, not later stage, maybe in next week itself, we will study more about, not more about, Thevenin, Norton, and there are other theorems like superposition. These are the most used theorems that we use. Now, one thing to note here is that although it is mentioned as DC network theorem, these theorems are applicable in AC circuits also. In AC circuits also, these are applicable, but there are certain conditions, which is that the supply has to be pure sinusoid, and the circuit is at steady state. You will get to learn the techniques and methods of how to solve AC circuits. Once you know that, you can use all these theorems in mm, the AC circuits also. The same thing. Okay. So go ahead, as usual, I'll start the session with doubts from you. If you have any doubt from this week or previous week's lectures, you can ask. I hope you have watched the lecture videos before coming to the doubt clearing classes.
For in the lecture videos, there are several questions which are that asked us to solve. So I have solved the question. So will you be solving it? Like there are some problems, how to tell them specifically.
Where are the problems given? This year's assignments?
No, so not assignments in the video lectures. The lecture number 11, 12, and 13.
Okay, wait, I have to check then. I am going to solve some problems. I'm not sure whether these problems are those problems. Let us do one thing. Let us complete these problems, and if we have time, then we'll look into those problems. As of now, tell me your doubts. No doubts? Okay. Lectures 11, 12, and 13. Okay, later on I will ask you at which moment to look at in those lectures, and then we will solve the problems maybe. Let us look at the problems now in hand. But before that, no doubt. All right. If you have no doubt, then we will directly start with the questions. So they have given in this question two circuits. And the question is, which of the following circuits is valid? Now, circuits are valid, all of them, but there are values of current and voltages everywhere. So looks like we have to verify from there whether there is something wrong. So let us look at the circuit, first circuit now. They say 9 ampere current is coming this way, out of which 2 ampere is going out. So this should be 7 ampere, but they are writing it 6 ampere. So clearly circuit 1 is not correct. Okay. And if we look at the other circuit, no current is given, except this looks like it's a voltage problem. Let us see. If we apply KVL in this loop, it matches. See, 35 equals 18 plus 17. So KVL in this loop is correct. And if we apply KVL in the other loop, it should be 17, increase of 17 plus increase of 26 minus 9. This is not equal 0 in this loop. Right? So this circuit is also not correct. Now the any doubt? Okay, we'll go to the next question. We have a circuit with a constant current source and a voltage controlled current source. No, not voltage controlled current source, 2AX current controlled current source. The voltage drop across that current controlled current source is Vx, and the current source has a current of 2Ix, where Ix is the current of this branch. And we have been asked to find out the value of Vx. Right, so we will try to, so all these circuits try to solve with as minimum variables as you can take. Okay? What we'll do is we will instead take a 3 ohm resistance here. Okay, we will take this as 3 ohm resistance and ignore this one. Right, same thing. Now if you apply, okay, let us see how much we can do first without writing equations. So 2Ix current is coming and Ix goes away. So Ix current flows in this branch. Ix flows and 8 ampere gets added to Ix. So 8 plus Ix flows here, here, here also. This is 8 plus Ix. Now out of 8 plus Ix, 2Ix goes away. So the current going down in this branch is 8 minus Ix. Right? So this much we can make out from the circuit. Now we have to solve for Vx and Ix, two variables. Now you see, if you look at these two nodes, these two loops, not nodes, one is this one and another one is this one. Can you write KVL? Yes, we have all informations to write KVL. And both the equation will involve Vx and Ix. So we can solve for Vx and Ix, right? So let me name the loops. I call this loop as loop 1 and call this loop as loop 2 and write the KVL for loop 1. Right? We will start from here and go down. So first what we will do is we'll give voltage polarity marks. If this is the direction of Ix, then voltage polarity like this. If this is a direction of 8 minus Ix, then polarity is like this. For 2Ix, polarity is like this. Now if I write the KVL,
So we can solve the same question by using node analysis too, right?
should be, yes. All of them are the same thing basically. Node analysis is nothing but applying KCL.
No, we'll be marking it like one should be marked as ground.
Yes, you can mark any point as ground like this. Okay, let us see. We'll try to do this with node analysis also. But node analysis means you have to take another variable, right? I think this will be easier with mesh. Which node do you want to consider for the node analysis? Let us
So
do
we
it with mesh, then we will see if we can do it in an easier way with node analysis. Okay. So we'll write voltage drop, we will write negative, voltage rise, we will write it positive from this point. So it's a voltage drop, so minus 4 Ix, then a voltage rise, so 3 times 8 minus Ix, again a voltage rise, Vx, then a voltage drop of 2 Ix times 1, sorry, drop minus, times 1 equals 0. This equation is correct. Drop, so minus, rise, again drop minus. So what we have is minus 4Ix, minus 3Ix, minus 2Ix, 4, 3, 7, 2, 9. Minus 9Ix plus 24 plus Vx equals 0, or Vx, let us keep it like this. Equation 1. Any doubt, or do you think anything is wrong? Looks correct. All right. Now the other one we will write for loop 2, the top loop here. Again, we will mark for the polarities. If I close like this, polarities are like this, and others we already have. So drop minus 3ix. Again, drop minus 8 plus ix times 2. Again, a rise plus vx, and a drop minus 2ix. Is this correct? Minus 3ix, drop minus 8 plus ix times 2. Kiran, please mute yourself. Minus 8 plus ix times 2, another drop. Vx rise, again a drop of minus 2ix. Okay. Then what we have is minus 3. Okay. Minus 3, minus 2, minus 2, minus 7. 7ix minus 16 plus Vx equals 0. Is it correct? Minus 3 minus 2 minus 2, 7 minus 16 plus Vx. So these two equations we have in our hand. We have to solve for Vx. Thing is, initially we can very easily find out Ix by eliminating Vx, although you have to find Vx. If you quickly do this, 1 minus 2, if you do, what you will get is minus 9 plus 7, so minus 2 Ix plus what, 30, 40. 40 equals 0. So Ix is 20. Now, how much? From 1 we can say minus 180 plus 24 equals Vx. I'm sorry, plus Vx equals 0. So Vx comes out to be 180 minus 24, which is 160, 156. So in this zone, right? Quickly tell me if you have any doubt. Yes, Kiran, go ahead.
So where did you get that minus 2ix in the second node equation?
Once again, in the second equation, what?
So in the second node equation, where did you get that plus bx? It's fine, but minus 2ix, where did you get that?
The second node starts from here. Say I have started it from here. Can you see the blue dot I'm drawing? Large blue dot. From this place I'm starting. Now if you
Where
go along this resistance, this is the minus 3ix, then 8 plus ix times 2, then this source, then this resistance, and you stop here.
Okay, I didn't see that minus 2ix. I'm sorry, sir.
Yeah, no problem. So there are 4 elements. 4 elements are here. This problem with node analysis will be difficult, I think. There will be too many unknowns. Let us see if we can do it with node analysis. Okay, maybe instead of just taking unknowns, we will try to derive as much as we can first. Let us see. So let us take a ground first. Say I am taking this as ground, 0 volt. Again, we will take this as 3 ohm. Okay, and this is not existing. Now, if this is 0 volt, then we don't know this current. We know this current. Ix, if this is Ix, then the voltage of this point must be 4Ix, right? And this is 4Ix, and there is a drop of 2Ix. So this is 6Ix. All these are voltages, okay? Because I am multiplying the current with a resistance figure. So dimensionally they are voltages. So this was Ix, high voltage 4Ix. 2Ix is flowing through this 1 ohm resistance. So 2Ix rise here. 4 plus 2, 6Ix. And we know that there is a drop of Vx here. So this one is at 6Ix minus Vx. Okay. Now if this is at 6Is minus Vx, then what? We can find out this current. Oh, sorry. 6Ix minus Vx by 3. That much current is going, and plus Ix, 6Ix minus. Anyway, what I am doing is not node analysis. I'm just trying to reduce number of variables as much as I can. So what we are getting from here is 18Ix minus Vx equals 24. Is it matching? No, not matching. You see one thing here in this problem, in the way we have solved this 8 ampere source 8 ampere source we did not use anywhere in our calculation. Means had it been 10 ampere, 12 ampere, whatever, our results would have been the same. No, we used here 8 plus Ix we used, sorry. Then it should be, oh no, this is not 18Ix, this is 9Ix. This plus Ix is 9Ix. 9Ix minus Vx, sorry, 24. Is it matching? Yes, this is one equation we are getting. And what else? This voltage we do not know, do we? 2Ix, Ix. Yes, we can find out. This is Ix. So a drop of 3Ix. So this voltage is again Ix, right? Ix was flowing in this branch. Yeah. If this voltage is Ix and this is 6Is minus Vx, the current through this is 6Ix minus Vx minus, or the other way around, maybe if I draw in that fashion, then Vx minus 5Ix by 2. This much current is flowing in this direction. No, it is getting too much complicated. We are not going anywhere, I think. Can we find anything? I think we have written almost everything we can. Can you think about an equation here? No,
Can
actually
we
the
mark
Mhm.
one and then can we solve it, sir? I mean, I have written the equations like
No, one more equation we need. No, which one is that? Looks like again we have to apply another KVL, or is there any option to apply a KCL? See, if I let us see if it works. If I apply KCL here, what will happen? If I write Vx minus, sorry, 5Ix by 2, I'm just trying to see whether I am getting a different equation or the same thing is coming back. Minus 2Ix equals 6Ix minus Vx by 3. So minus 611 Ix, Vx minus 11 Ix by 2. Hey, how is it 11 Ix? 4, 9. Ix by 2 equals 6. Ix minus Vx by 3. So 3Vx minus 9, 27 Ix equals 18 Ix minus 2Vx. 5Vx equals how much? 30 plus 1545 Ix. Vx equals 9 Ix. Is it true? It is not true. Uh-huh. 3Vx measurement equals 6 into 12. X minus 2Vx. So 5Vx is not 45. 39 Ix. Is it true 5Vx? Should be 380. Can you find the mistake anywhere? Anyway, looks like somewhere I have written something wrong. So in this way, see, basically what we are doing is uh, we are applying KCL basically you can say at this node and this at this node, and getting some equations which we can solve and get the final answer. But in this question or in this circuit, KVL or mesh operation is much easier, as it seems. Or can you quickly find out what is the mistake? I can't see anything wrong here. I don't know. 6ix. Anyway, you can find it out. Just take a screenshot of this and see if there is some mistake anywhere. But this is the approach. But anyway, this, since we have a current source here, this is stopping us from applying a node analysis here easily. Had this been a voltage source, we could have easily done a node analysis here, I think. We would know this voltage, this voltage, this voltage. Yes, should have been easier. Anyway, anything else you want to ask from here? Or are you doing it yourself? Okay, we'll move, go ahead then. Just do it once again. These things you write, this node voltage and branch currents you write, and apply KCL at 2 points. All right, we'll look into this problem.
The question
Yeah,
was in the lecture video also, and it was done using node analysis. So I'm trying to solve it by that method.
this one you are saying?
Yeah, a very similar question was in the lecture video as well.
Maybe. Thing is, see, there are two problems here. One problem is this current source. We do not know the voltage across it. Second thing is, in this branch, there are two parallel elements. Sorry, two series elements. Had this been one element, we could have assumed some current and and written the node voltage. That too we do not have. So this is it more difficult. At the end, see, at the end you have to solve the circuit in the way it is the easiest. It's not about applying the node analysis or something.
So the very previous day asked you a question regarding whether, like, how to verify whether all the currents or the voltages we are finding it as correct or not. So
Hmm.
in a video which was not of NPTEL, it was said that we can verify it using the node analysis.
That is one way. Like you find out all the voltages and currents. See, thing is, do not solve the circuit once again. Rather, what you can do is write down the, or in the circuit itself, write down the current at all the branches, and then also you can write down the voltage drop across all the elements, or maybe the node voltages. Okay, then at all the nodes you verify KCL. At maybe in some loops you verify, or maybe all the loops if it is not very complicated circuit, you verify the KVL. Do not just go for solving it once again. Just all the nodes you can check for the for KCL. If I write down all the currents and check for KCL, it should match at all the nodes. Yeah, at all the nodes. Or should we look into it? Okay, let me look into it once again and see where the problem is. We started from here, 0, 4ix drop. So this is at 4ix, and 2ix drop in this resistance. So this is 6ix minus vx, so 6ix minus vx by 3 plus ix by 3, which gave us 9ix minus v equals v equals 24. This was correct. This matched from here. Okay, 9ix minus vx by 3. And if this is 4ix and ix must be flowing, so 3ix drop, this must be ix. This must be ix. Then how did we get this current? We had 6ix minus vx here and ix here. So ix minus this, so minus 5ix plus vx by 2. This way we got this current. Okay, let us write another equation. Since this one did not work out, we will erase this and try to write another equation. Let us write KCL at this node and see if this thing match. So KCL at this node gives us 8 plus ix equals vx minus 5ix by 2. And let us see whether we get a different equation. So what we get is 16 plus 2ix equals vx minus 5ix. So 7ix min no. Anyway, whatever. 7ix minus vx plus 16 equals 0. I think we already got this equation before. No, anyway. So 7ix minus vx is 16. Now where does it match? 7ix is 140 minus 156 is minus 16. Yes. So basically now you have two equations. If you solve this, you will get the same answer. This and this. We did this by applying KCL. Node analysis is nothing but KCL, right? 2 points we applied KCL. At this point, we got equation 1 from this node and equation 2 from this node. Okay. And if you talk about verification, let us say with this.
Another equation is minus vx minus 24 plus 9ix equal to 0.
What minus Vx?
Minus vx minus 24 plus 9.
Go again. I couldn't hear you properly. Minus Vx minus 24.
minus Vx minus 24 is equal to minus 9Ix.
Minus Vx minus 24 equals minus 9Ix. Yes, that we got here. Equation 1. So these two equations, if you solve, we will get the same answer. True. Should I go for the next question?
Yes, sure.
Okay. In the circuit given in figure 3, determine the power associated with the 4-volt battery. Where is the 4-volt battery? Here, this one. How much power is associated with it? How much it is delivering or absorbing? We have to find out. Now, we solved such a circuit in the last class that this branch will carry no current, because if some current goes, there is no path to return. So this branch will not carry any current. So what we can do is this part of the circuit we can simply ignore, right? There will be some currents here, some currents here, but we can ignore this part of the circuit. We have to look at only this part. That is clear? Okay. Now we will apply KCL and KVL in this circuit and find out the current in the 4-volt branch. See one thing, if you look into this loop, look at this loop. This loop has two voltage sources and one current and one resistance. So we can easily find out the current flowing through this resistance. 30 minus 10 by 7. So we have 20 by 7 ampere of current flowing in this direction, downwards. Is it clear how it came? Simply it is the 7 ohm is having 20 volt across it in this fashion, 20 volt. So this much current we have. Here 20 volt, and that is in additive with this 4 volt. So 24 volt is coming across the 8 ohm resistance like this. 24 volt. So I will erase this. So this must be 3 ampere. This must be 3 ampere. And what else? 10 volt and 4 volt. So 6 volt must be coming in this way. So this must be 2 ampere. Now 3 ampere was coming, out of which 2 ampere is going out. So this must be 1 ampere. So the power associated is definitely 4 watt, and whether it is supplying or delivering, supplying or absorbing. Supplying or absorbing?
Delivered.
Supplying.
So it is delivered.
Yeah. Okay, the option is delivered. Same thing, delivered is applying. See, this question is good enough, like KVL is good enough to solve this, KVL and KCL. You have to choose the loops judiciously. If I had started, say, this problem, if I had started by solving this loop, that would be difficult. I had to take some unknown variables. Not difficult, I had to take some unknown variables and solve them later. Rather,
Sorry to interrupt. Cursor and your words are not matching, so we're not getting it very.
hmm, what is not matching?
The cursor and the words are not matching, sir. It's becoming very difficult for us to catch it.
Oh, they are not matching. Just a second, I will log in from other device. That is something that is beyond my control. I'm checking from other device. Okay, I will try to mark for you. Okay, when I show some part, I'll mark for you like this. Is that fine? Okay. So instead of starting with this loop, this upper loop, I will show by drawing. Instead of starting with this red colored loop, we started with this green colored loop. What advantage it gave us? We could easily find out the current in this resistance. In this resistance. Because we know that there is 20 volt appearing across this resistance, so we can find out the current. Now if you look at the red colored loop, we know that 20 plus 4, 24 volt is coming across the 8 ohm resistance, so we can find out its current also. Now we go to the downwards loop. We could have done this also earlier, because 10 4 voltage sources are there. uh, since there are voltage sources, we need not worry about how much current is flowing through them. We can simply apply KVL and say that there is 6 volt drop across the 3 ohm resistance, and hence it is carrying a 2 ampere current downwards. Now when we apply KCL at this node, we can find out that 1 ampere current is flowing through the 4 volt source, and since the current is leaving the positive terminal, it is delivering power, 4 watt of power. Okay. Any more question? Should I go to the next question then?
Yes, sir.
Okay. So this network is there, power associated with 10 ampere source in the circuit.
After you are done with all the questions, please give us some information on how to redraw circuits. Because there are questions where the need arises, so please help us in redrawing circuits.
Redrawing.
Yes, like redrawing the circuits, like rearranging the circuit basically.
Rearranging, one example we saw last day, right? Do you remember? Rearranging. Where is it? This one?
Yes,
Yeah. So it's all about marking the nodes with the same potential, then take the elements one by one and make sure all of them are in the redrawn circuit connected across the same potential. That's all. Okay. We'll see if we get some more complicated circuit,
we
we'll look into.
start the point and then we can find it, right?
Hmm. Like this one, do you need redrawing of this circuit? I don't think so. This is anyway quite simple. Or redrawing will make it easier. No, I don't think. The power associated with the 10 ampere source is how much? Okay, let us see if we can do this with node analysis. Okay. Let us take this one as 0 volt. And this one I take as Vx. I think I have to take another variable somewhere. Vy I have to take. If this is Vx, then this is Vx plus 10. And yes, I will take Vy here, say. And if this is Vy, this is Vy minus 20. So we have to write two equations. We have to write two equations. Let us start by node analysis of this point. Okay. So we will write the currents flowing out. So currents flowing out. 0 minus Vx by 2 plus 0 minus Vx minus 10 by 1 plus 0 minus Vy by 4 plus 0 minus Vy plus 20 by 3 equals 0. Okay, so this is one equation. Just keep it like this for now. And what should be the other equation? Where should I write? Let us write KVL at the outermost loop. So we have minus plus here, and if we write another minus plus, then this is Vx minus Vy plus 10. Are we getting something or not? No, I don't think this will give us anything. No, this will not give us any equation. It will simply give us 0 equals 0. Could you see it that is this will give us 0 equals 0? If you just keep adding, everything will cancel up. You will get 0 equals 0. So what else can you apply? Any idea? Let us use this. What is the current here? And say what is the current here. So this current is Vx plus 10. And this current is minus Vx by 2. How is it coming out like that? No, this will also give us 0 equals 0. We'll simply just 10 equals 10 or something.
So if we divide, like if we use the upper half and the lower half, then also the equation is coming 0.
Okay, let us do one thing. We have to find out the power associated with this. Let us see if we can find out this one, Vy minus Vx minus 20. Let us multiply this equation with 12. So it comes out 6Vx minus 6Vx minus 12Vx minus 120 minus 3Vy minus 4Vy plus 80 equals 0, right? I multiply this equation with 12. Yeah. So what do we have? Do we have the same coefficient for Vx and Vy? Luckily, no. We have minus 18 Vx minus 120 plus 80 minus 40 minus 7 Vy equals 0. We are not getting a good equation out of this. What else to take? I think this one also will be easier with mesh. Let us try with mesh. Okay, and we'll see later if we can do it. So we have seen that we need two variables. We'll go back to that. Let us see. So I will take, let us say, I1 ampere of current flowing in this branch. So 5 was going this way, I1 goes out. So this is 5 minus I1. So this was 5 minus I1, out of which 10 goes away. So what we are left with is minus 5 minus I1. Sorry, small I1. That is going through this branch. That's all we have from here. And what else we have? Let us say this is I2. I2. So 5 goes this way, I2 goes this way. So this must be 5 plus I2. 5 plus I2. So 10 was coming. 5 plus I2 goes this way. So this must be 5 minus I2. Is it correct till now? Yes. So now if we calculate KCL, if we do KCL here, we have all incoming currents. So I1 plus I2. Okay, so KCL gives us nothing. 5 minus I2 minus 5 minus I1 equals 0. So what we have, what we can say from here is these things are correct. Now we have two equations where two nodes where we know the voltages. There is a nodes with the voltage sources. One is this one. I will write this one. Other is this one. So if I write like this, then what we have is 20 equals 4i2. 4i2 drop, yes, rise is drop, and a rise, so minus i2 times 3. This one equation you have. So what you got here is 20 equals 4i2 minus 15 plus 3i2. Oh, we can solve i2 here separately.
I2 is coming 5.
How much? 5, yes.
5.
5. Then all this one also we can solve separately. This also we can still solve separately. So 10 equals drop I1 and rise. So plus. Are we getting I1 equals 0? Can you check once? Or you did some mistake? 10, this is I1. So 10 equals I1.
No, we're not getting 0, we're getting 5.
Again, you are getting 5.
5
Wait.
by 2.
5 by 2. Wait, I'll write here. Start from here. So it's increment of 10, then a drop of I1, again an increment of, tell me if this equation is correct. Why am I getting 0? No, I am getting I1 equals 0. And I think it is matching because you see, we got I2 5 ampere. So if this is 5 ampere, 5 ampere current flows here, and there is no current in this branch, 0 ampere, right? If I1 is 0, then there is no current here also, 0 ampere. And minus 5 ampere flows in this direction, means 5 ampere flows in this direction. So basically, this branch and this branch, they are not carrying any current. I1 will be 0. Okay.
Sir, can you
Now,
please explain your method once more? Like which loops did you take?
wait. We have two loops here where we have the voltage source, right? One loop is this, another loop is this.
So the main problem is your cursor is not matching with your words. So whatever you're taking is not appearing at that very same moment.
No, there will be a delay. There are so many paths in between, so many elements in between. I'll talk slowly maybe. That's something beyond my control. So what I'm saying is, there are two loops here where we know the voltage. So these two loops only we can apply the KVL. Now what we found out here, that this current was 5 ampere, I2 was 5 ampere, we found. And we took I1 here, which is 0 ampere through the 1 ohm resistance. Now if you look at this one, 5 minus I2, this one was 5 minus I2. Now I2 is 5 ampere, so we have 0 ampere current here. And again, if you look in this circuit, in the 2 ohm resistance, the current was minus 5 minus I1. I1 is 0, so the current is minus 5 ampere. We took it from right to left. So basically in the 2 ohm resistance, we have a current flowing from left to right. So 5 ampere current flowing in this way. So it matches. No current through these top and bottom branches, 1 ohm and 3 ohm resistance. 5 ampere current comes in and goes out. Now, if you look at the bottom triangle, that is, if you look at this triangle, we have a drop of 20 volt here and a drop of 10 volt here. Let us take a drop of V in the 10 ampere current source and write the KVL. Now if you write the KVL, you will get 20 voltage increase, minus 20 drop, again minus 10 drop. So 20 increase, 20 drop, 20, how much? 10 drop, and increase of V, that comes up to be 0. So V equals 10. So basically the current source we have 10 ampere and a voltage of 10 volt. So it is 100 volt delivering. Sorry, 100 watt delivering. Is it clear? Okay. This way, this thing, I don't know where to write another equation. Something we got here. And what else to write? Can you explain why it is 0? We've wrote the current equations. We took, see, here in this branch, we assumed the current to be I1. And in this branch, we assumed the current to be I2. Right? These two unknown variables we took. Now, based on these two unknown variables and other current sources present in the circuit, we can write down the current expression for the other networks. Now, from there, what we do is we write down two KVLs. Write down two KVLs. One in this loop, because we have a voltage source here, this loop, and other one in this loop. These two KVLs we write and solve, which gives us some values of I2 and I1. Now, once we substitute the values of I2 and I1 in the circuit, we find out that whatever current is flowing through this 4 ohm resistance goes out through the 2 ohm resistance, and no current flows through the 1 ohm and 3 ohm resistance. Okay, we'll go to the next question then. This one, this is a voltage divider circuit or potential divider, whatever. The no load value of V naught is 15 volt. When the load resistance R naught is attached across the terminals A and B, V naught drops to 10 volt. This thing we discussed last day, that these are non-linear. The output voltage depends on the load. Find R naught in terms in ohm. So basically this is a potential divider or a voltage divider circuit, and the load is supplied through the AB terminal. Okay, we connect the load at the AB terminal. Now when there is no load, which is the no load voltage they're saying, it is 15 volt. So from here, what can we find? From this information, we can find out the value of R first. So 60 volt, and at no load, this is 15 volt. So this must be 45 volt. So the voltage drop across R is 1/3 that across 30. So R must be 10 ohm, right? Or you can do it in a more methodical way, that if this is 15 volt, then the voltage across 30 ohm is 45 volt. Then at no load condition, the current I is 45 by 30. So that much current is flowing through this R and causing a voltage drop of 15 volt. So R you get 10 ohm. This way you can find out. So basically the potential divider is now in a situation that the upper voltage, this one is 30 ohm, and this one is 45 and 10, 15, but this is 10 ohm. But as soon as you connect this is connected, the voltage division now changes, because now here in means in 30 there is R and R naught. So this lower voltage, this voltage now even reduces, because the voltage in the resistance, okay, we will see. So V naught drops to 10 volt. Why does it drop? It drops because one more resistance comes in parallel to R naught. So equivalent resistance is now less. So there is less voltage drop across the combination. So V naught is reduced. Simple. Now V naught drops to 10 volt. So if now this is 10 volt, this is 50 volt. Now we have 1/5 of the voltage drop here. So definitely R parallel to R naught is 30 by 5, 6. So AB by A plus B is how much? R is 10. 10 times R naught by 10 plus R naught is 6. From here we can find out R naught. 60 plus 6 is 15 ohm. Is this clear? Is it clear how I got this value R parallel to R naught equals 6? This value how I got, is it clear?
So clear.
Okay. All right, we'll go to the next question then. The circuit shown in figure 6, find the value of R in. This one we have to find out. What have they given? They have given the voltage 24 volt minus 12 volt. See, in such cases, in case you are confused or you cannot find it out properly, what you can do is you can imagine a circuit like this. You can imagine a circuit like this. In reality, we develop plus and minus voltage like this fashion only. 24 volt, 12 volt. This ground that I have drawn here and this one, they are the same. Because here is a ground. Here in the question, they have given a ground and they have written 24 volt here. That means this 24 volt is with respect to this point. Okay. So if you want to write KVL and all, you can assume, not assume, you can imagine a circuit like this. Actually, it is developed like this way. We'll try not to use that loop. Okay, let us see. We have to find out the what value of R in. Okay. Value of R in we have to find out. How to do? So 100 micro is going in this way. Let us do it this fashion. Let us say some current I was coming in this path, out of which 100 micro goes away. So we have I minus 100 micro in this path. So the total voltage drop across the resistances 100 kilo times I plus 100 kilo times I minus 100 micro is 36. 24 minus 12, 36. Basically, I am applying KVL in this loop. Okay. Now, can you solve for I? 100 kilo I and 100 kilo I, two are here. So 200 kilo I minus how much? Okay. So this 3 goes away. Am I correct? 100 kilo times 100 micro is 10. Sorry. So we have I equals 46 by 200 times 10 to the power minus 3. Forty-six by 200 minus 3. 3 times if I do 10 to the power 6, this should give me the microampere. This 230 microampere. What is happening? 230 micro. So basically what we have is 230 micro coming down this way, 100 goes away, so 130 micro comes down this way. Right now what we can do is, I think I am doing it in a difficult way. There should be a easier way. Let us see. We can find out the voltage at this node. The voltage at this node is simply 24 minus 100 kilo, sorry, 24 minus 100 kilo times 230 micro. 1 volt it is coming. 1 volt. So 1 volt, as I said, this is with respect to this ground. So if 1 volt can cause 100 microampere of current, so 1 by R is 100 micro. So R should be 1 by 100 micro, which is coming out to be 10 kilo. Can you think about an easier way? I think I made this more difficult. No, it's fine, I think. There are kilo and micro, so the calculations become a bit difficult. The solution is clear.
Sir, I have one doubt here.
Yeah.
Uh, can we use voltage divider rule here, because 100K and 100K equal resistances? 36 can we take as the loop voltage, as you have written KVL already?
No, you cannot write voltage divider because there is a tap here. Because the same current is flowing, but you have something going out. So the current in this resistance and the current in this resistance, they are not the same.
Yes, sir, understood. Sorry.
You see, voltage divider is not applying or being applied also. 100 kilo, but the node voltage here is only 1 volt. So here you have a drop of 23 volt,
Okay, sir.
and here you have a drop of only 1 volt. Sorry, not 1 volt. It's 36, so rest of it 13 volt.
13 volts. So across 100K is 13 volts, then 100K and R in are parallel.
Yes,
So
since they came into parallel, the equivalent resistance dropped.
So can it be as 13 volts must be
Not
the drop
parallel.
across?
So
Not
we
parallel,
cannot
sir.
call it parallel. No, not parallel.
Not parallel. Okay. Yeah, minus 12
Because this
volts
is
was
not
connected.
grounded.
Yes, yes, sir. Yeah, understood.
Okay, any doubt? All right, we'll go to the next question. This one is a bit complicated. I don't know how to solve this. In the circuit shown in figure 7, the voltage drop VD is how much? Why is VD there? How to solve this? Delta star will be helpful. Let us see. If I can do delta star, then these two resistance come in parallel, sorry, series. Then I can write this as voltage source and resistance, then they come into series. Then this will become something like this. One resistance will come. Then we can solve it. Could you get how I will convert this to this? We'll see. First of all, I have to find out the formula for delta to star conversion. Wait a minute, I will search Google. I do not remember delta to star conversion formula. Hmm, where is the final result? Yeah. So they are saying the for result is RA equals R1 R2 by summation of the R's. Delta to star, right? So if this is the delta to star formula, then all see here we all have 12 ohms, right? 12, 12, 12. So basically these three resistances will be the same. So if I call this R, then R will be 12 times 12 by 12 plus 12 plus 12. So 3 times 12. It should be 4 ohm.
40. No,
40.
48. 8, sir. I'm sorry, 4 only.
Okay. So if it is 4, so now this delta is no more here. Okay, let me draw it again for you. Just right hand side I will draw. You have the star between these 3 points. Okay, all of them are 4. Now this 5 ampere parallel to 6 ohm, this I will write 6 ohm series with 30 volt, and here we have a 6, right? So basically this circuit now boils down to, we have 48 volt, 2 ohm, 4 ohm here, 10 ohm here, 10 ohm here, 30 volt here, this. right? Now let us take a current I here. So the current I flows through this I, and can we do it in an easier way? KVL, Norton's theorem, can we apply? Okay, let us forget. Let us just do it directly. I, and say I minus I1 goes through this and I1 goes through this. So what we have is 48 equals 6I plus 10I1, and we have 30 plus 10 times I minus I1, increase. Can you solve this and tell me quickly?
Sir, in the loop one,
Hmm.
don't we take 10 ohms and 30 volts source also in KVL one?
We could have taken yes, but I took the other part, so it's I can have only one element.
Yeah, understood, sir.
Easier. Same thing you will get.
Sir, I1 is coming 3.
3. Did you do I1 is coming 3? Okay.
And
If
no, and I is coming also 3.
I is coming 3, should be 3, right? If this is 3, this is also 3. Yes, right. I minus I1, 3 minus 3 is 0. 330 matches. 18 plus 30, 48. So 3.
No, minus 3.
Minus 3? No, if it is 3, then only I cannot be minus 3. I can be minus 3. Anyway, are you getting I equals minus 3? If they both of them are 3, then only it is matching, right? You have 18 here, you have 30 here, 48. Here also, you have 0 here, you have 30 here. If
No,
both
it's
of
coming
them
3.
are, yeah, both are 3. So what we have is 3 ampere current flowing. So how much is VD? Tell me.
Minus 6 volts.
Minus 6 volts, because VD direction is shown in this way. But if the current flows like this will be at the higher potential. So it's minus 6 volt. Any doubt in this question?
No, sir.
Okay, then I will go to the next question. In the circuit, determine the power associated with the dependent voltage source. Okay. So whatever voltage comes across 5 ohm resistance, 5 times or 3 times of that will be coming here. And we have 3 ampere of current here. So let us just solve the circuit. What else? Easy one. Looks like an easy question. Let us take this current to be I. And if this is I, this is 3 minus I. Okay. Well, not a very easy question, because voltage drop across 3 ampere we do not know. That is fine. Just a minute. We have one equation with I and VR. Let us write anyway. No, we have two equations. So what we have written here, from there we can write that VR is minus 5I. True? This we can write. This is our first equation. And then we can write KVL. We can write 10 volt increase plus VR increase. If this is I, and okay, we have found out that this is 3 minus I, and this is like this. So increase, increase, increase. So again, is the equation correct? Yes. So we have 10 minus 2 VR plus 6 minus 2I equals 0. What do you have to find out? Do you have to find out power associated? So basically you have to find out I. We will replace VR with minus 5I. So if I replace VR with minus 5I, then I have 10I. So 8I is minus 16. I is how much? Minus 2. I is minus 2. Okay. Now power delivered by this source is how much? 3 times VR, okay, times 3 minus I. Any doubt in this? This is the power delivered. 3 times VR times 3 minus I, the power delivered. Now VR is minus 5I, so VR is 10 volt. Okay, so what we have is 3 times 10 times 3 plus 2, so 150. So we took it as power delivered, and what we got is positive. So power is actually delivered by this source, dependent voltage source. 150 watt power it is delivering. Clear?
Yes, sir.
Why did I write power delivered? How did I know that this multiplication will give me power delivered, not the power absorbed? How did I know that?
Current is entering the negative terminal.
Yes, so my 3 minus I ampere current, this leaves the positive terminal. So their product will give me the power delivered. So if it is positive, power is actually being delivered. If it is negative, then power is being absorbed. Say, for example, if you look at the 10 volt source here, our current came negative. So this 10 volt source is actually absorbing power, 20 watt of power it is absorbing.
Uh,
Okay. Hmm.
okay, I is negative, so it is absorbed.
Yes.
Yeah, I
I
understood, sir.
I took I as going up, but is actually going down. So
Yes, yes, sir.
2 ampere current is flowing. All right. So we'll go to the next question if there is no more doubt. How many questions do we have? 1, 2, 3, 4. My goodness. Let us see how much I can do today. In the circuit shown in figure 9, determine the minimum value of K such that power dissipated in the 2-watt resistor does not exceed 50 watt. Why this 2-watt resistor, 2 ohm resistor, this one? So looks like we have to find out the power dissipated here, which is Ix squared times 2Ix squared. This should be less or equals 50. So basically what we have is Ix or mod Ix should be less or equals 5. Mod Ix because we do not know which direction current will flow. Can you tell me, just outside electrical engineering, what is this?
Mod X.
Mod X. So similarly, we had Ix squared less or equals 25. So square root mod Ix is less or equals 5. Okay. Can we solve this? Let us solve this. Let us see. K we do not know. Okay. So we have a current controlled voltage source here. Ix is coming this way. So 6 ampere comes this way, of which Ix goes out. So the current that we have here is 6 minus Ix. And here we have 8 ohm 16 volts. So this current has to be 2 ampere. So 6 minus Ix was coming, 2 ampere goes away. So this is 4 minus Ix. Anyway, we do not need this. Just take this as 16 volt. That is enough. And we will draw the voltage polarity. Then we will write KVL. Start from here, this point. So increase in voltage, 2Ix increase in voltage, drop in voltage, 6 minus Ix times 4. Again increase in voltage, Kix. Again a drop in voltage, minus 16, 0. Right? Yeah. So what we have is 2Ix plus 4Ix, 6Ix minus 24 plus Kix minus 16 equals 0. So what we have is 6 plus K times Ix is 30, 40. So Ix is 40 by 6 plus K. I think what they want us to do is just make a square of this. So P is 2 times 40 by 6 plus sorry, K squared, right? Minimum value of power is this. We have to minimize this. Or in other words, we can maximize this. No, am I making it more complicated? Wait, we need not do all this.
Sir, can we take ix as 5 and solve for k? I'm getting as 2.
Not like that. So, okay, ix we have here 6 plus this, now mod ix. So, mod of 40 by 6 plus k less or equals 5. So the thing is, modulus of x less or equals 5, what does this mean? Does it mean this?
Yes, sir.
It means this, right?
Yes, sir.
So what you can write from here is minus 5 less or equals 40 by 6 plus k less or equals 5. Simply write minus 1 and 1. This becomes huh, this becomes 8. Now minus 1 greater or equals 6 plus k by 8 greater or equals 1. Tell me if I am doing anything wrong. These things I am doing after many years. Ah, no, sorry. Minus 6. 2. How is it coming? So where does k lie? Is this is 0, this is 2, this is minus 14. K should be either here greater than 2 or less than. So this is the range of k. What is the question? Determine the minimum value of k. See, this is why they mentioned this. Otherwise, the answer would have been minus infinity. Minimum value of k such that power does not exceed 50 watts. So k is 2. Minimum value of k. You circle both of them. Okay. All right, we'll solve one more maybe today, and if we have maybe next class we'll solve the others. We have 3 more minutes left. So in the circuit shown in figure 10, determine the value of IA minus IB in amps. Why do they have to ask like this? IA minus IB. Do you guys remember this thing? Two voltage sources in series, and there used to be one equivalent. You can write this time this plus this times this. I think I remember it was something like they're in the same direction here. So 50 times 2 plus 20 times 8 by 20 plus 2. Something like this was there, right? 100 plus 160. This was the equivalent voltage and the equivalent resistance was parallel 40 by 22. Can someone confirm?
Yes, sir.
I think the equation was like it was like this. Okay, now 2 ampere current goes this way. 2 ampere current goes this way. I think this is easier. So basically what we have is, see, IA was coming in this fashion through this node, and there is something here, and IB was coming, and of which 2 ampere goes out and 2 ampere here also goes out. So basically what we have is IA minus 2 equals minus of IB minus 2. No, but this is giving us IA plus AB. IA minus 2 is going that way, and IB minus 2 goes this way. So IA minus 2 should be minus of IB minus 2. Yes. What I have written is correct, right? Oh, I thought I can solve this without solving the circuit. Now I have to solve the circuit. Okay, let us do 20 volt, 10 volt. Oh, it's not that difficult anyway. So what we have is 20 volt. I will draw only the part that we need. Okay, 10 volt and 130 by 11 volt, 40 by 22 ohm. 130 by 11 volt, 40 by 22 is 20 by 11 ohm. And there are two more resistances here also. But we can apply KVL only at the outer loop. So if we apply KVL only at the outer loop, what we have is how much current is flowing here. In this direction, if I write 20 minus 10 minus 130 by 11, this much voltage, whole divided by 20 by 11. Someone quickly do and tell me. 10 minus 130 by 11 whole divided by 20 by 11. Minus 1.
4.
4, not minus 1.
Yeah. Sorry, sir.
Minus 1. So basically what we have is, in this case, 1 ampere is going in this direction. So IB must be 3 ampere and IA must be 1 ampere. So IA minus IB is minus 2 ampere. Okay. Assuming that this equation, this formula what I used is correct. I used it maybe 5 years, after 5 years, I don't know. All right, then if you do not have any more question, we will stop today here. These 2 questions we will solve next Monday, and then we will go for the questions of the next week.
Thank you, sir.
Yeah, thank you.